Hello everyone, welcome to this lecture of the course Digital Electronics and Circuits. And in this lecture, we will be talking about K-maps or Carnot maps. So let's get started and let's see what K-maps are. So basically, when I say K-maps, it's like shorthand notation for Carnot maps. Correct? So basically, K-maps are nothing but these are graphical devices which are used for simplifying Boolean expressions. Basically, here we try to relate input to output and we try to simplify an expressions to ensure that a circuit minimization is there. We don't want to have extra AND gates or gates, NOT gates. We just want to ensure that our circuit is minimized, and that's why K-maps are a way of reducing a circuit. And usually, as a rule of thumbs, right, these are usually useful up to 6 variables, and we will see why, right? And when used properly, Carnot maps can reduce expression to a MSP, right? Basically, we saw something like sum of products last time, and we know that okay, minimal sum of product is something which we intend to get as a result of K maps, and there are minimum number of. So basically, a sum of products is nothing but it will be something like ABC plus DEF plus GHI. So our aim over here would be to have minimal number of product terms and each product is having minimal number of literals. Correct? So basically we want to minimize the number of entries of our operation which we will be doing, and second aim over here will be to minimize the number of literals which we have in each expression, right? Basically aim is to achieve two level of minimization. Minimization. And how do we do that? Via using K-maps, which can help us reduce number of literals and in each of the every term and number of the product terms. Correct? So basically, how do we look at K-maps, right? So let's get started with that, right? Let's start with a three variable function, and let's say that we have a truth table for a three variable function. So let's assume we have function f of x, y, z, which is a three variable function, and the number of entries for this could be f of x, y, z. What are the possible combinations? 0 0 0 0 0 1 0 1 0 0 1 1. Right? Let's suppose we have this function, and what we will do over here is we simply say that we have a truth table like this. When we try to convert this truth table to a K map, we simply say that each row of truth table, each row, each row of a truth table corresponds to or maps to one square in K map. And there are a few other properties, right? Adjacent squares in K map differ by only one variable. Correct? Now basically, right, if I have to form a K map for this three input function, what I would simply do is I will create a box with two rows and four columns, and what I would do is I would say like if x is 0 over here, x is 1 over here, this is 0 0, this is 0 1, right? This has to be 1 1 because of this property or this rule of K-maps where we say adjacent square in K-map should differ only by one variable, right? If this is my K-map mapping of a truth table, so basically if you know it, differ by one variable is something which we saw in the very first lecture in terms of reflected code or gray code, and so this is something like which is pretty useful when we have to do error detection and error correction, right? So if we say, okay, this is my truth table, this is my K-map with each and every with variables mapped onto K-map and each and every adjacent variable differing only by one variable, right? One value. So what this will become? This will become something called as M0, right? X000 is nothing but, if this is 2, this is M0, this is M1, this is M3, this is M2, M4, M5, M6 and M7, right? So basically this is how we have mapped each and every entry of a truth table with a K-map. And what we can do over here is, I hope this one is clear, right? This part is something which I want to spend some time on also to ensure that you guys understand it correctly, right? So let's pick up a different color altogether. So what we have done over here is, we are mapping a truth table to a new kind of a table which we are calling as a K-map, and each entry in this truth table is mapping to an unique entry in the K-map, correct? So my 000 M0 is mapped to this particular entry, my M1 is mapped to this entry, and since the K-maps rely on the fact like the adjacent squares change only by one variable, when we go from 0 1 we have to go to 1 1, right? So basically M3 would be mapped, this is my M3, this will be mapped to this column, and uniquely if you see M2 goes over here, and M4, M5, M6 and M7 are different blocks of this particular table. So we map truth table to a K-map table, and adjacent square differ by only one variable. Now comes the most important rule in terms of like how do we minimize the circuit using a K-map. When we have to minimize a circuit using a K-map, a simple funda is, we combine all the squares having a value 1. Okay, so let's take an example. Let's assume the function which we saw in the beginning. Let's assume I have a function called function f of xyz, which is equal to, let's say, summation of m 1 5 6 and 7, correct? So basically what does this mean? The term 1 0 0 1 1 0 1 1 1 0 and 1 1 1 1 5 6 and 7, these are all 1. Now if I have to map this to a K map, right, how would I build a K map? I would simply create a block for a 3 variables with x, these are yz. If you see 8 blocks for 8 entries of truth table, 0 1 0 0 0 1 1 1 1 0. Here my M0 is mapped, here M1, M2, M3, M2, M4, M5, M7 and M6, right? Now if we have to fill up this table with using a truth table, how do we go about it, right? So what we can simply say over here is, my M1 is 1, right? So this is 1. My M5 is 1, my M6 is 1, my M7 is 1. So M1, M5, M6 and M7 are 1. The rest all are zeros. 0 ones are the something which we will not care about right now, because K-maps rely on the fact like combined adjacent ones, right? So basically if you see, if we have to just write this function, right, how do we write it? We will write it as x bar y bar z plus xy bar z plus xyz bar plus xyz. This is how we will end up writing this function in a normal form, right? Now what we will do is, whenever we have this thing, what we can do is, if you see, if we go from m0 to m1, if you see my y remains 0, only z changes, right? And K-maps rely on the fact like we can group together adjacent ones and we can form squares and rectangles based upon that. But whatever we group has to be in the multiple of 2 raised to power n, where n could be 0, 1, 2 and so on. That's the K-map funda. And simply as we spoke, right, K-map, we are trying to minimize two things. One thing is we have to minimize number of odd terms, that is basically number of input of OR gates we have to minimize, and then second thing which we have to minimize is number of products in each and every literal. So if we have to look at this circuit, right, how we can minimize it? So basically what all combinations are possible where we can have uh, 2 entries, 4 entries, or 6 entries, right? So basically this is one combination, this is another combination. Okay, now if I combine m1 and m5, what will be the value? If you see, x is changing from 0 to 1, so x is, which we, and but yz remains constant. So summation of m1 plus m5 will always yield us something like 0 1, which is like y bar z, and summation of m7 plus m6 is nothing but, if you move from here to here, my x remains constant and my y remains constant, both are 1, it will be xy. So I would say my this particular circuit which was represented using this could be minimized to a circuit which is like xy plus y bar z. We can go by the same way over here also. We can simply say, okay, let's take xy common, z plus z bar will become 1. Over here what we can do is we can simply take y bar z common, we will get x plus x bar. So if we do Boolean minimization, we will get y bar z plus xy here as well. But what we have achieved using K-maps is we need not go into that entire Boolean set of expressions and minimization. We can directly map a truth table to a cake map, and then depending upon certain rules, we can combine ones, and the number of ones which we could combine is usually 2 raised to power n plus 1, where n can vary from 0, 1 or 2, or we can simply say it's 2 raised to power n, where n could be 1, 2 and so on. We can only capture, or we can only group entries in the form of 2 entries, 4 entries, 6 entries, and this is something as an example which I showed you that okay, we ended up getting a reduced circuit altogether for this particular situation. Correct? This was one of the examples, and now let's assume one more example, right? Let's assume an example where we have a function where we say that okay, we have a function called f of x, y, and z, where which is equal to summation of m of 2, 3, 6, and 7. This simply means, what is my function? My function is 2 means 0, 1, 0, so it's like x bar, y, z bar, x bar, y, z, plus 6 is nothing but x, y, z bar, and x, y, z. Now if I have to minimize this, right? How do we minimize this? Let's form a K-map. Let's create a bracket, square, rectangles, right? And then we can say, okay, this x is represent x, this x is represent y, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. Now let's fill entries of 1, right? So basically we already saw that each entry is mapped to a particular number, and we saw that 2, this is 0, 1, 2, 2 is 1, 3 is 1, 5, 6 is 1, 7 is 1. Rest all are zeros. In K-maps we don't care about zeros, so if we have to look at a grouping, we are getting a grouping of 4 variables over here. And if you see what is changing from here, x is changing from when we go from top to bottom, x is changing. When we go from left to right, we have only y being constant, z being changing. So this particular function, if I have to reduce f of x by z, would be equal to y. And basically, look at this, how simple was this, that we were able to say that okay, this is equal to y. The same thing which I have to do over here, right? In such a case, I have to take x bar y as a common, this will become 1. Then basically this will become xy, then I will take y common, x plus x bar is 1, so this will become equal to y. If you see, this is pretty easier via k terms, like via k maps, right? Over here the only difference is, as compared to previous example, is what we did is we combined 4 minterms as opposed to 2 minterms in the previous example, right? So, and one more thing, right? How do you see, basically the main fundamental over here will become, how do we decide the grouping? How do we decide the groupings, right? How do we decide how many minterms we should group together, whether we should group 2, 4, 8, 16, right? Because bigger the group, if you see, since we have 4 terms over here, which is like 2 raised to power 2, right? What we saw is the final output we got for xyz, which is a 3 variable, is only a 1 variable. So basically, bigger the groups, smaller will be the number of literals in each and every term, right? And smaller the number of groups, smaller will be the lesser will be the number of product terms. So basically, if we have to look at the terms, right? If we have to decrease number of sums, basically decrease number of OR gates input, right? OR gate inputs. What we have to do is we have to minimize number of groupings. And second thing is if you have to reduce or minimize number of literals in each product term, right? This would be that we have to make larger groups. Look for larger groups with corresponding ones. This is the fundamental over here for K-maps, right? And how do we decide upon the groups? Let's take one more example over here. If we look at this particular example where we have a K-map, right? And in this K-map, we have something like 1, 1, 1, 1. It's like 0. So basically O1, let's assume we have 3 outputs O1, O2 and O3, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. Now let's assume if I form a group like this, there are 4 groups, but this is neither a square or not a rectangular group. So basically I said we can have a group of 2 raised to power n, right? Elements or 2 raised to power n variables where n can be 1, 2 or 3. But if you see over here, I created a group of 4 terms, but this group is neither square nor rectangle, right? Will this benefit me? Do you think this will benefit me? No, this will not benefit us because eventually if you see, if we move, there is nothing common in this grouping. Neither O1 is common, neither O2 is common, neither O3 is common, right? So basically, but if we break them into 2 groups, this group and this group, you will see we have something common. In this particular group, O1 and O3 remains common, and in this particular group, O2 and O3 remains constant. So I can do a reduction using that particular techniques, right? And third thing is, right, if I don't look for a 2 raised to power n numbers, if I'm looking at 3 numbers, right, let's assume that we form a group of top 3 entries where we say that, okay, we want to add 3 numbers. Bigger the groups, lesser will be the number of each literal, right? That will also not be a valid thing for us over here because if you see, right, if I end up creating a group out of these 3 entries, what would happen? We do have O1 as common, right? But eventually we can't neglect the interdependencies of 0, 1, 1, 0, 1, 1 just to form a one term, because if you see this will be nothing but this is ending up as like 1 is nothing but 0, 0, 1, right? So this is x bar, y bar, z. 2 is nothing but 0, 1, 0, which is like x bar, y, z bar, and 3 is x bar, y, z, right? So do we have any reduction over here if we try to form a group as such? No, we don't have any reduction over here at all. Correct? So this is the basic concept over here, right? So we need to have only square and rectangle terms with larger number of groupings and minimum number of products. So basically, if you see, for ensuring that we have minimum number of OR gates, which is our first requirement, we need to ensure that we cover all the elements or all the ones with minimum number of groupings. And second concept is to ensure that we have less number of literals in each product term. We have to create a longer or larger groups, because when we create larger groups, our output would be dependency upon less number of variables, right? So this is one of the examples which I wanted to share with you. And just to be careful, just to be comfortable with K-maps, right? More the examples we do, more comfortable we would be. Let's assume we have a function called x bar, y bar, z bar plus f plus x, y, z plus x bar, y, z bar, right? So basically we started with this thing. This is nothing but min terms. or truth table, right? We start with minterms or truth table. I am trying to recap what all we have learned till now. Then what we do is we will plot a k-map. K-map is simple for a 3 input variable, where we simply say, okay, we have x represented in this axis, y and z in this axis. We have 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. Right, and now we populate the entries over here, and let me use a different pink color. So basically x bar, y bar, z bar is nothing but m0. This is nothing but m1. This is m7, and this is like 110 m6. So m6 and m7. So basically what we simply see is how many adjacent ones. This is a group of two available. Can we have a bigger group? Not yet, not right now. So this is one group. This is another group. This group corresponds to what? X remains constant, x bar. And over here, did anything remains constant? Yes, y bar. Right. Similarly, what remains constant over here? X plus y. So what is this? Xy plus x bar y bar. Right. And as we already talked about this, the tricky part is to find the best number of groups of minterms, right? Let's take one example for this method. Let's assume that we have this particular minterm K-map with this particular composition. Right? 1, 1, 1, 1, 1, 1. How do we group them? Right? So basically remember our aim. Our aim is, number one aim is we need to have less number of OR inputs. So basically if that is the case, what we need to have is we need to cover everything with minimum groupings, right? With minimum terms. Our second aim is to minimize number of products in a literal term, single literal term. So we have to have larger groups. And the next is something which is like a requirement from KMF side. We need to have a group of 2, 4, 8, so on. And it has to be the square or rectangular groups, right? So looking this into mind, how do we group this, right? So if you see, we definitely have two groups which are visible to us at the top level, right? And those two groups are these ones. This is one group, and this is a second group. Okay, so let's assume I choose these two groups. What I will end up getting? So I will end up getting, let's assume this is x, y, z. This group will correspond to x because x is 1, and this corresponds to what? X bar x. This will be x bar plus y. Correct? X being this one, and x bar x being this particular entry, and x bar by being x bar and y. Okay, this is one example. So we got two groups, and we got a good amount of length 2 and 4, square and rectangle. How about I tell you that one more combination is possible over here, where we can simply do is we can simply look for something like this being one group, and instead of making this as a second group, we make a larger group as a second group. And if this is done right, what would be the output in such a case? Output in such a case would be x, first group remains the same, and the second group will be what? The only common thing is y. So this will become x plus y. Does this make sense? So basically, right, what I'm trying to showcase using this is we can have overlaps in the groups as long as bigger groups helps us attaining less number of literals in each product term. Because if you see, as we moved from, if you see, like as we moved from one part to the another part, right, as we moved from xy to this one, basically this remains constant, right? This entry remains constant. But what we did is, with a larger group, we were able to convert x bar y, one AND gate requirement, to a simple y operation. So we saved upon one AND gate, right? So Overlapping is possible as long as it helps us create larger groups. But in case of overlapping, right, I should not be creating extra groups that, okay, let me create a bigger group, I can create a bigger group. So, but let me have extra entries, because if I add extra entries, right, my this first requirement will go for a toss. So basically we saw one particular thing, like we tried to minimize the number of groupings, but we try to maximize the size of each group, correct? Now let's have one more practice exercise, right? Let's say we have one more example where we say we have a function where we have terms like this is one, this is one, this is one, this is one. How do you end up creating groups for this, right? Let's look at this. So what are set of groups are possible? This is one set of group which is possible. This is another set of group which is possible, right? And this is a single one. So what will be the value in this case, right? 0, 0, 0, 1, 1, 1, 1, 0, 0 and 1. This is x, y, z. So my first group would be what? X bar z, plus my second group would be y bar z, plus my third group will be x z bar, right? This is one example. Do I have one more example? Yes. So, but let's see one more situation over here where can we have some different set of groups possible in this particular case? Yes, we have, but that will not lead to a minimization circuit, right? For example, if I say let's go with a technique where we put a group of these two, then this, then this. If we go by this mode, right? Basically, this term, which was still now in the previous expression, came out to be y bar z, will now be replaced with what? X y bar z. So we have an extra entry, one more additional literal. So this will be not a preferred one, correct? And I wanted to show you one more example where I wanted to tell you that like more than one solutions are also possible, where you can get two solutions, but both of them are minimal sum of products. For example, if I create something like this, right? Let's assume we have an example where we have 1, 1, 1, 1, and 1. Right, so what would happen in such a case? If we look at this, our first set of possible combination is, okay, this is one combination, this is another combination, this is another combination. What is the second set of combination which I can have? The second set of combination which I can have over here is something like this. This being same, but this one goes with this one. So basically, instead of having this particular group, I can have this particular group. There is like they will both the things. If I put both the situations, right, both the solution for the first term would be y bar z plus yz bar plus x bar, and solution for the second one would be y bar z plus yz bar, and the third term would be different. It will becomes xz, right? But both of them would give the same output. Both the maps here will contain the fewest and the largest possible groups. Resulting expressions are both minimal sum of products, and they have same number of product terms and the same number of literals. Correct? So this is like basics of K-map. I spoke about multiple concepts over here, and we mainly looked into a three variable K-map. Now moving ahead, I just want to touch upon a four variable K-map, right? If we have four variables, right? We have a function f, x, y, z, and alpha. It is a four variable function, and how many possible minterms we can have? We can have 2 raised to power 4 minterms, which is equal to 16 minterms, right? The 16 minterms, the K-map which we will form for this would be a square K-map with 4 rows and 4 columns. This will be something like I'll be showing you. Let's assume we have x and y over here and z and alpha over here, right? If this is the case, what we can do for this particular K-map is we can simply say this we have already seen 0, 0, 0 1 1 variable change 1 1 1 0. Same thing will be applicable here 0 0 0 1 1 1 1 0. So basically this will be nothing but m0 m1 m2 m3 m4 m5 m7 m6 m8 m9 m10 m11, and similarly this would be m12 m13 m14 and m15. The mapping of truth table to K-map remains similar, just that we have a bigger block, and that's why we said like that's why in the beginning, right, when I spoke about K-maps, I said this visualization, when we move on to 5 variables, we will have like 16 min terms, and when we move to 6, we will have 64 min terms. 5 variable one would be like two K-maps superimposed on top of each other. 6 one would be like four of these superimposed on top of each other, right? The basically analyzing that becomes pretty difficult, right? Now let's assume we have a 4 variable expression and we want to simplify it, right? Let's assume we have a function f which is equal to m0 plus m2. It's a 4 variable one, m5 plus m8 plus m10 plus m13. How do we go about minimizing this? So basically first step would be we would be creating a K-map. Let's draw it cleaner, right? So right, okay, we have xy, z and alpha, and then let's see, we have something like 0 0 0 1 1 1 1 0 0 0 0 1 1 1 1 0. Now let's populate the entries. So basically m0 is nothing but this one, m1 m2 m4 m5 m6 m7 m8 m9 m10 m11 m12 m13. M13, correct? Now if we have to minimize this circuit, let's try to form groupings. This is a simple one, this is simple one, 1 1. If you see, right, so what will be our first group? Our first group would be something like let me choose a color. Okay, so basically this is definitely a group we are going to have. Then we have set of possibilities. We have a 1 over here, we have a 1 over here, we have 1 over here, we have 1 over here, right? If we do this, how many terms we will have? 1, 2, 3, 4 and 5, right? However, is there is a set of minimization possible over here, and if you see, right, if we try to wrap this around, if we try to wrap this particular thing around, let me show you via pointer. If I say let's wrap, will this form one group? Yes, this will form one group because in this particular group, your alpha remains constant, right? Your alpha remains constant over here, as well as your y remains constant, correct? So basically, if we go with this particular setup, so our output would be basically my alpha is constant, so this is alpha bar, and my y is constant, this is y bar into alpha bar, correct? Plus this particular term, which is nothing but y into z bar alpha. This is a particular solution for this 4 variable K map. So this is what I want to talk in this lecture of K maps. Basically, let's get used to it. And in the next lecture, I will be talking about something called as prime implicant and essential prime implicants, which would help us further ensure that our analysis of K map have been proper and we have not missed out on any term. Thank you.